In today's lesson, we are going to look at solving exponential equations. And in this first part, we're going to look at how to do that with common bases. We're going to look at how to not to do or how to do it with bases that aren't common in a later lesson in another unit. But for right now, we want to look at solving exponential equations with common bases. So the first thing we want to do is just rewrite some of these as a power with the base 2 or with base 3. So for 8 we can rewrite as 2 to the power of 3. 16 is 2 to the power of 4. 1 over 8 is 2 to the power of negative 3, or 2 to the power of negative 4, to the power of negative 5. These other ones on the right, I can rewrite these as a power with base 3, because 27 is the same thing as saying 3 to the power of 3. 81 is 3 to the power of 4. When they're fractions, just a negative exponent. So kind of the same pattern as the previous ones. So we're going to be using that to help us solve equations or exponential equations, but we want to kind of just revisit how to solve equations in general. So to solve an equation means to isolate the unknown variable. So in this case, I want to get x by itself, right? So I need to isolate it. So there's different ways you might have learned, right? Either you move these separate terms to the other side, and it becomes the opposite operation, or you cancel it out. So minus 4 minus 4. One side cancels out. We get 2x equals 11. Now we divide by 2 because that's the opposite of multiplying. We get x equals 11 over 2 as our final answer. So that would be solving a regular equation, but we want to solve exponential equations. So let's consider the following equation here. 2x to the power of x minus 1 equals 8. I can rewrite 8 so that it has a common base, or a base of 2, like such. And when I have common bases, as we see here, this is a base 2, this is a base 2. When we have common bases, we can just compare the exponents. Right? So we have common bases. So therefore, we can compare exponents. So when we compare exponents, we essentially just take x minus 1, and that has to equal 3. Right? Because we have equivalent bases or common bases, we just compare the exponents. In order for them to be equal, x minus 1 has to equal 3. Now I can go through and solve this equation, add 1 to both sides. That cancels out, and we have x is equal to 4. So that means in this equation, x equals 4. So essentially, that's what we're going to be doing when we're solving for these common, or for solving these exponential equations. We want to get a common base and then compare exponents. So we have a couple of examples that we're going to work through. So let's take a look at the first one. 2 to the power of x minus 5 equals 8 to the power of negative 2. Well, 2 to the power of x minus 5 isn't going to change. I can rewrite 8 as a power with base 2. 8 is the same thing as 2 to the power of 3. And then that is raised to the power of negative 2. I have to use my power rules to simplify here. So this becomes 2 to the power of negative 6. And now I have common bases. So therefore, I can compare exponents. So x minus 5 has to equal negative 6. I add 5 to both sides. One side cancels out, and we get x is equal to negative 1. So that means the solution for this equation is negative 1. Try B. Same idea, right? We have the first one, 5, 3x plus 1. I have 1 over 25, so I could rewrite that as 1 over 5 squared. That still doesn't give me a base, or sorry, to the power of x. That still doesn't give me a base 5, so I need to convert this to flip the fraction. So 5, 3x plus 1 doesn't change. This fraction now becomes 5 to the power of negative 2, so kind of reversing it. And then that is all raised to the power of x. So 5, 3x plus 1 equals 5 to the power of negative 2x. So again, using your power rules. Now we have common bases. So therefore, we can compare exponents. So 3x plus 1 equals negative 2x. I need to get rid of the x's on one side. I'm going to minus 3x minus 3x. We get 1 is equal to negative 5x. I'm going to divide by negative 5 to cancel it out. We have 1 over negative 5 is equal to x. So again, that is our solution. So again, the hardest part should be just converting to get common bases, right? Because you have to use a bit of your power laws, and you have to know what some of the numbers can turn into with common bases. Like, so that's how we kind of did that little warm up, looking at what numbers we could turn into base 2 and other numbers with base 3. C, 4 to the power of 5x minus 2 equals 8x to the power of x plus 1. So neither of these can become bases of 4, right? 8 or 4 to the power of anything doesn't really give us 8. So we have to convert both of them. And both of them can be converted to powers of base 2. 4 would be 2 to the power of 2. So 2 to the power of 2 to the power of 5x minus 2. 8 is 2 to the power of 3, which is then raised to the power of x plus 1. Because I'd be multiplying powers, this would be 2 to the power of 2 times 5x minus 2, which is equal to 2 to the power of 3 times x plus 1. I can convert that or simplify that or expand it, but I'll do that later once I get rid of these bases, because now that I have common bases, I can compare exponents. So 2 times 5x minus 2 equals 3 times x plus 1. Now I need to solve. So distributive property tells us we have to multiply the number outside the bracket to everything on the inside. So 10x minus 4 is equal to 3x plus 3. Now I can solve, or continue to solve. It's minus 3 from one side, 3x, minus 3x from the other. 7x minus 4 is equal to 3. Add 4 to both sides. It's 7x is equal to 7. Lastly, divide both sides by 7. We get x is equal to 1. So again, we're converting our powers so that we can get a common base, and then once we have a common base between the two sides, then we can compare exponents and solve for x. Let's take a look at the last three. And we will leave the last one for you to try on your own. But 9 and 27, so again, we kind of have to think about what powers, or how can we write these as powers with the same base. They do share a common base of 3, because 9, or 3 to the power of 2 is 9. The 2x plus 3 is still there. And 27 can be written as 3 cubed raised to the power of negative 2. I can use my power laws, because when it's a power to a power, it would be multiplying. So this is the same thing as saying 3 to the power of 2 times 2x plus 3 equals 3 to the power of negative 6. Again, now that I have common bases, I can compare exponents. So 2 times 2x plus 3 equals negative 6. I have brackets, so I have some distributive properties to worry about. 4x plus 6 is equal to negative 6. Minus 6 from both sides. 4x equals negative 12. Divide by, not negative 12, sorry, divide by 4 to get x by itself. We have x is equal to negative 3. So again, getting the same base, using our power laws to simplify it, right? We don't want any brackets around our base, right? So that's why we use our power to a power rule. Then once we get our common base, we compare exponents and solve for the unknown variable. E16 to the power of 2x plus 3 equals 64 to the power of x minus 1. So again, these can be written as powers with base 4. You could also do 2 as well, but then you're going to end up having larger numbers, right? So it might be easier to use 4 instead. So 4 squared, it can be replaced 16. The 2x plus 3 is still there. 64 can be written as 4 to the power of 4. Or not 4 to the power of 4, sorry, 4 to the power of 3. And then the x minus 1 is still going to be there. So we have 4 to the power of 2 times 2x plus 3 equals 4 to the power of 3 times x minus 1. We have common bases now. So therefore, we can compare exponents. So 2 times 2, 2 times 2x plus 3 is equal to 3 times x minus 1. 4x plus 6 equals 3x minus 3. Cancel out the 3x's on one side. Do the same thing to the other side. So we get 1x plus 6 equals negative 3. Subtract 6 from both sides. We end up with 1x is equal to negative 9, or just x is equal to negative 9. So try to do the same thing for the last one, right? Try to rewrite these two powers with a common base, and then compare exponents and solve for the unknown. So to help you get started, I'll at least tell you that your common base will be 2. So I'll give you that much information, and then you can work from there. I do recommend you try pausing the video to try to go through this question. So again, pause the video, and we'll come back with an answer. So coming back, this is what we should get. We should get an answer of x equals 1. Right? Convert it to a common base, right? So 16 can be written as 2 to the power of 4. 8 can be written as 2 to the power of 3. Use our power to a power rule to multiply your exponents. I didn't multiply them until I just compared it until after I got the common base, and then I distributed just to make it a little bit easier and have more room to work with when I'm just looking at the exponents. And we go through and we solve for x, and we get x equals 1. So again, the main thing from this lesson is understanding that we can solve exponential equations if we have common bases, and that some numbers can be rewritten as common bases, or with bases with the same, or powers with the same base. We're going to be looking at in future lessons how to do that when they don't have the same base, using technology, and then as well as using what we call logarithms in another unit to solve these exponential equations. But for right now, just focus on being able to convert so that you have powers with the same base, and then compare exponents to solve for the unknown variable.